All right, so what I'd like to do here is set the stage for and ultimately prove what is called the definition of a derivative, right? So we've been playing around with this idea of secant lines and tangent lines, and the problem that we have is that, as we saw in the GIF activity or the GIF activity, is that when the secant line approaches the tangent line, everything is okay, but once the secant line becomes the tangent line, it disappears. And the reason for that is that there's no longer, if you think of the slope of the secant line as rise over run, there's no longer any run, right? There's no horizontal distance that we can measure to get the slope of the secant line. Therefore, it's a tangent line. So we have this divide by zero situation. And I can't get this entire graph on the screen here, I guess, but what I've got is a curve. So we've got the curve in black. And then we have these secant lines that we'll call PQ, then PQ Q1, and then PQ2. We'll call this Q2 here. All right. And what I'm doing is sliding these secant line closer and closer to what is the tangent line here in purple at point P. All right. And the x value location of P, I'm going to call that location A. And then the horizontal distance from A to wherever those points are, I'm going to call A plus H. In other words, this distance here is called H. All right, and so what I'm going to do also is, and I think I'd like to do this on a sheet of graph paper. Okay, I have graph paper. So that gives you sort of a visual of what we're thinking about here. We're sliding these secant lines down and trying to turn them into tangent lines. Let's set this up, and you may want to put this in your notes. It's up to you, but I'm proving something here. Sometimes students get a little worked up when I don't tell them that ahead of time. So we got this. All right, so there's our y-axis. So our function will be y equals f of x. It doesn't really matter what the function looks like. We are going to sketch a function that is just going to look sort of nice for our purposes. So it's going to look something like this. Okay, so some arbitrary function y equals f of x. At A, I'm going to put a point on the curve. That point will be a comma f of a. Again, some arbitrary point. And then some point further down the x-axis. And that distance down, we're going to call h. So this distance here is h. And this x value then will then be a plus h. All right, so there's a plus h. Then the question is, well, what is the point on the curve going to be then? Well, that point, we'll call it Q. Actually, let's call this point P. Let's call this point Q. This would be a plus h, comma, f of a plus h. All right, so everything should be okay here. We've just labeled our 2 points. Now, what we have been doing is finding the equation or the slope of the secant line. I'm going to put that in as a dotted line here in blue. Okay. All right, so there is our secant line. And finding the slope of that is not too terribly difficult. We get 2 points. We use the slope formula. I'm going to write out what the slope of line PQ would be, but I'm going to write it out generally. Okay, so it would be this. The slope of PQ is equal to, all right, well, slope formula. So f of a plus h minus f of a divided by the x-coordinate. So a plus h minus a. Right, so a plus h minus a. Okay, so let's simplify a little bit. So we have the slope of PQ is equal to, so on top nothing will simplify, f of a plus h minus f of a divided by, so a plus h minus a, the a will drop out. Okay, so a minus a is 0, so I'm left with just h down here. So there's the slope of PQ. But what we really want is ultimately the slope of the tangent line, and I should have got my, oh, I do have my ruler. All right, so what we really want is the slope of the tangent line, which is here in red. Now, to figure out the slope of the tangent line, what we're going to do is let h get smaller and smaller and smaller, and in other words, we're going to let h approach 0. Well, how do we denote that mathematically? Well, we've already talked about this idea of a limit. And so we are going to write the limit as h approaches 0 of that fraction. So f of a plus h minus f of a divided by h. Okay, so that limit right there is the slope of the tangent line at P. And I should have written that, sorry. This is the slope of the tangent line at point P. Okay, and instead of saying the slope of the tangent line at point P over and over and over again, what we call that is f prime of a. So it's f with an apostrophe, f prime of a. Okay, so limit as h approaches 0 of f of a plus h minus f of a divided by h. And there you have one of the most important expressions in calculus, the definition of a derivative, of slope of the tangent line at a point. And so this is, I guess I should say that too more clearly. This is the derivative of the function at a. All right? In other words, it's the slope of the tangent line. That's what a derivative is. The slope of the tangent line at point P, which in our case here is at a f of a. So in other words, we would write f prime of a. This is the slope of the tangent line at a is equal to whatever this limit turns out to be. And we'll do several examples of that. But as we're using this limit right here, I just want you to know exactly where that comes from. It comes from this idea that comes from in this graph right here. All right. So there's the definition of a derivative, slope of the tangent line at any given or at a given point.